I'm building another spool valve engine. This one will have a 1/2-inch bore, unlike the last one, which had over a 0.8-inch bore. In other respects, it'll be quite similar, with one notable difference. The last one had a 1/4-inch upright above between the base and the top of the engine block. This one is going to have a 1/2-inch upright, 1/2-inch wide. That will allow me to put a longer bearing in it, so it won't have so much lateral force on the bearing. I'm going to center drill it and then step drill it up to 15-30 seconds, and then I will bore it from there to 1/2-inch. The background noise you hear is the fan, and got a dehumidifier running, but all that's going to be subsumed when I turn the mill on. Notice that I'm using collets for the drill bits. That's because I'm out of vertical space. I could use the Albrecht keyless chuck with the center drill, but it's not. It's too long. The Albrecht's too long to allow me to get it in there with the vertical space I've got with the workpiece mounted in the vise. So I've gone to collets. Of course, one might ask, how am I going to stick a 15-30 seconds in a 1/2-inch collet? Well, I'm not. I bought a 15-30 seconds inch collet just for this task, and I've already measured, tested the little, what is it, 2-inch boring head with the insert-based bar. It'll just fit in there with the vertical space I've got. So we're good to go, I think. How deep am I going? Oh, about 1.5 inches will be deep enough. I remove material from the sides and then expose the bottoms of the valve body hole and the cylinder later. Here's 3/8 before we go to 15-30 seconds. that's got it. Here we go with the 15-30 seconds. I'm turning this at 371 SFM. That was an easy cut. We'll bore it next. As it turns out, I do not have a insert-based boring bar that will work in this little boring head. I've got this cemented carbide bar, which will take an 1.5 inch cut, which is about what I need, a little less maybe. And I'm going to give that a shot and see how it works out. I'm turning it at 231 SFM, which is 1800 RPM on this mill, and the balance is good so far. This is my scratch cut. Looks pretty good. So I will take 10 thousandths and see what it looks like and come back later. This is the final cut. In order to obtain a good finish, I'm only taking 4,000. Not many chips. Finish looks good. Well, the bore looks great, so I'll put a telescoping gauge in it and mic it. In my hands, telescoping gauge is probably not the most accurate thing I could use. But as I mentioned, the diameter of the bore is not super critical. I just didn't want to make it huge like I did last time. So here's a .497 minus plug gauge. Fits in there real nice. So this makes me happy. I'm going to drill the hole for the valve, drill and ream it. I'm going to ream it, I believe I'm going to ream it 1/4 plus. I had to go to plan B on creating the hole for the valve. I simply don't have enough vertical space to get a reamer in if the workpiece is mounted in the vise. The reamer's long. So what I'm going to do is stick it here against an angle block. And I'm not going to worry too much about getting the angle block aligned because I'm going to drill a hole and it not too important. It could be off like that or that. It doesn't make any difference because I'm just going to drill a hole. So I'm going to align it with this square. And then proceed to clamp the workpiece in with a C clamp, maybe 2 C clamps, I don't know. It is important that the workpiece be perpendicular to the table, parallel to the axis of the spindle. So I've got a DTI in here, which is, of course is good to a 10,000ths, and I've already bumped it into place. And as you can see over the travel of the valve, which is, well, I can't remember, it's inch and 1.3 or something like 1.3. I'm getting zero deflection of the pointer, no movement on the scale. So if I can tighten it down like that, it'll be good. I've got 2 clamps on the workpiece. It's in there nice and solid, and I'm still perfectly aligned. Oh, I guess not anything's perfect, but this DTI won't register anything. Alright, I'm ready to ream it. Instead of using a 0.25 over reamer, which I measured at 0.2516 with a mic, I think that's close to being right. I'm going with this 0.2505 reamer. And then I will turn the valve body to fit if necessary, if a 1/4 inch piece of drill rod doesn't fit right. So I'm going to turn the reamer at 117 SFM. That looks great. Notice I forgot to point out, but notice the brass shims I put in to protect the aluminum from the C-clamps. I'm going to finish the surface later, but I still didn't want the C-clamp marks on. I'll polish this piece of 250 drill rod down to 0.2498, so I took 2/10 off of it. I stuck it in the lathe and used 220 grit followed by 600 grit to polish her back up. And I think it's going to make a good valve. Get a nice fit. I left it this long because I have a couple operations I need to do in the mill, and of course got another operation I have to do on the lathe to make the spool valve perfect. So this length will give me a convenient length to work with. I'm hogging out the material on the cylinder side to form the pedestal. I'm taking 50,000ths of cut. When I say pedestal, I mean the upright between the base and the cylinder and valve. Cut's going well. I'm about halfway there, a little less than halfway. I've got a line scribed right here. This is the end of the cut. So I've got this much more to do. I should have mentioned a while ago that I'm side milling. Of course that's obvious by now. I think this is going to be the last cut. It's 25,000. I believe that's going to be pretty close to my scribed line. Well, it turned out well. Next I'll do the valve side. I'll leave a 1/2 inch upright here. I flipped it over and I'm going to remove material on the valve side from about this point to this point. I've got scribed lines in both places. I hogged that side out. It went well. It went a lot faster than the other side because I took 100 thousandths per side milling cut. So this looks good. I'll clean it up along the clean up these tool marks along the length here with a 6 flute 3/4 inch end mill. It turned out well. This is the cylinder side. This is the valve side. Can you see the tool marks, the swirls? Can you see where all sides of the cutter are visible? That means the mill's in trim. I need to create the hole for the main bearing. It's got to be 2 inches from here, from the base, and of course I want it in the center. And I've already located the table such that it's that way. I don't think this hole has to be bored. I don't think the finish has to be great. I think good will do it. So what I'm going to do in an effort to try to make it good with a drill bit is I'm going to step drill it in 4 increments, well, in 3 increments, and then the final at a 1/2 inch, and take a look at the finish. If the finish is acceptable, I'm going to build the main bearing. If it's not, then I will bore it till just a bit till it is, and then turn the main bearing on the lathe to fit that hole. Turning the spindle at 2,950 RPM, which is as fast as this mill will turn. When I get up to the 1/2 inch drill bit, that'll be 350 some odd SFM. Remember, the pedestal is only 1/2 inch wide. That hole looks mighty fine. That's what the finish on that drilled hole looks like. Time to build the main bearing. I'm going to build it out of this bronze 932 stock. It'll be a little over 1/2 inch in diameter, so that it'll be a light press fit into the upright of the engine. And I will ream it to 0.2505, and if the drill rod that I have doesn't fit 0.2505, I will go to 0.251, see how that works. So the main bearing will be a little over 1/2 inch long, to give almost 25 thousandths protruding on each side of the upright, to act as a thrust bearing surface for the flywheel and on one side, and the crank disc on the other. I'm ready to ream at 0.2505 to ream to 0.2505. Good. I'm parting the workpiece from the raw stock. The workpiece is 0.550 inches long. That's the goal anyway. I'm using an AR Warner high-speed steel grooving tool, part of this. This main bearing hole in the upright is close to 0.5, a 0.499 plus plug gauge will fit, and a 0.500 minus plug gauge won't. So if I take this down to 0.5, it ought to give me a light press fit into that main bearing hole. So that's what we're going to do. This should be the last cut. Well, I took it a little too far on the 499.5. So let's see how that fits. Let's re-mic it. Get the same, so I'm going to chamfer that and see how it fits. Alright, I mic'd it at 499.5 and it won't fit, so I'm confident of what I mic'd it at, and I'm confident of the size of this hole, so that means I'm going to get a light press fit when I chop this baby off and press it in there. got a good fit with this test piece of drill rod. Now I'm going to press the main bearing into the engine upright. Of course, I've already got it set up. There, we're making contact, and it's pressing in very easily. Run into some resistance there. Have to take it out and figure out what the resistance is. Resistance was that I'd run out of room like this with the block oriented that way. I was pressing against the engine itself, so that wasn't any good. So we'll turn it like this and finish pressing it. I want to press it so that there's a, pardon me for hitting the camera. Okay, that's all the way in, so there'd be about 50 thousandths sticking out on this side since it's all the way in. What I want to do is have about 25 thousandths sticking out on each side. So I'll figure out a way to do that. I know this bearing is about 50 thousandths longer than this distance here. So I want approximately 25 thousandths on this side and 25 thousandths on this side. So this is a 25 thousandths inch feeler gauge, and it fits in real easy. Now it's got a little resistance, so I'm going to call that good, I think. And indeed, it's either good or very close to it. See, this will give me a thrust bearing surface on both sides. On this side for the crank disc, and on this side for the flywheel. I'm going to lop off a piece of 1/4 inch drill rod to use as the main shaft. May adjust the length of it later, but for now it's going to be 2 3/8 inches long. Clean that up a little bit more. I'll just do it with a file. The eccentric follower link is next on my list of things to build. Here's my pattern. And here's my jig. Notice that the pattern fits right on those 440 transfer screws. What I'm going to do is put this piece of brass plate on it like that and press them together so I can get some marks on the brass. Make sure I'm far enough in there. Hope I've got all the transfer screws set same length or close to it. There we go. One, two, three, 4, 5, 6. 1, 2, 3, 4, 5, 6. I got it. Should have mentioned that this jig is something I built earlier and showed its use in a previous video. So I won't show in detail how to use it now, other than to say I'm going to center punch these holes I've indicated, and then clearance drill them number 32 for 440 screws that I have here. And I'll bolt this to the jig, center it under the spindle on the rotary table, and then cut the eccentric follower link out with the mill. All 6 holes are center punched. Now I'm going to center drill them. I don't guess there's any reason for you to watch all this. They're center drilled. Now I'm going to drill number 32 clearance hole for 440 screw. Missed. I'll deburr this, and then after I do, I'll bolt it down to the, well, I'll center the fixture under the spindle first, and then I'll bolt this to it. If you're wondering how I center this jig under the spindle, it's easy. I've got a 1/4 inch over ringed hole there. I simply put a 1/4 inch piece of drill rod in the chuck and move this around till it goes in. Then it's centered, clamp it down, we're good to go. The jig is clamped to the table. The workpiece is securely bolted to the jig. Because of the alignment, I know that the center hole that we're going to have in a moment is directly under the spindle. I'm going to make the center hole a 1/4 inch to start with. Of course, then I will make it the proper size with an end mill and the rotary table. I'll offset the rotary table a 1/4 inch and spin it around, and while I'm cutting, and that'll give me a 1/2 inch diameter hole here in the middle. As you see here on my pattern. The reason I'm sticking a hole in it in the center is to have a place to go back to for 2 reasons. If I screw up, I need a way to get the whole thing realigned under the spindle. And number 2, I like to have a place to start the end mill and then offset the table a 1/4 inch while I'm cutting. And then I will lock the mills table back down and then rotate the cutter, or rotate the rotary table and wind up with that 1/2 inch diameter hole. It'll all become clear. Okay, I've just milled out the center part of the link. Just milled out this part right here. Next, I'm going to mill this section. Have to be careful and stop in the right place. Okay, I kind of make a little mistake here, but we'll recover from it. In laying this out, what I should have done is bolted this pattern down on my workpiece using my 440 screws, and then simply scribed the whole thing. I really need the long piece scribed. Don't really need this. Yeah, I could have used the circular piece scribed too. Like it is, I'm going to have to kind of guesstimate it, I think. We'll figure it out. The nice thing about using this jig is that I can take the workpiece off, do whatever I want to it, put it back on and resume where we left off. In this case, what I wanted to do is what I indicated earlier. I wanted to scribe the pattern, the complete pattern of the eccentric follower link using my pattern here, the one I've already built. So I'll do that. Then I'll take the pattern back off and continue machining. The important part is getting the sides right here, and knowing where to stop as I'm cutting this outside diameter. Alright, I've got my line scribed in there like I want. Bolted back down with these 6 440 socket head cap screws, and I learned from bad experience what happens if you don't secure a thin workpiece securely. Don't secure it securely. Does that make sense? What will happen is, especially out here on this long part, is that the end mill will lift the workpiece up, and you're liable to break an end mill, which I did, and ruin a workpiece, which I did not. So we're ready to cut the rest of it. I'll cut the outside diameter first. I've offset the table in the X direction. The proper amount is actually 0.406 inches, and it lines up with my scribe mark for the outside circumference of this thing well. The next step is to get this radius between the circular part and the shank, get this radius, get the end mill about where I want it. I can clean it up later with a file or whatever I have to. So if I'm a little short, that's okay. And then I'm going to have to plunge this end mill 0.0512 thousandths inch. I don't have any choice, but it'll cut. So that's what we're going to do right now. I'll set it. Let's go back over here. 0. We'll go back to where we were. Point oh 0.034. I want to go to 0.051. There we go. I'll lock it right there. Start turning. Did you think it's going to hit that side head cap screw? Looks good. Now, by trial and error, I will get the table, the rotary table, aligned with the x-axis and cut these two sides. All right, I believe I've got it lined up with the x-axis. We're going to take a cut. I'm going to feed by hand. Because the finish on the side of it's not important anyway. Good. Now for the other side, I'm ready to cut the other side. Notice I've got a clamp, an extra clamp now on the workpiece itself. It's preventing you from seeing most of the cut that I'm going to make. But what will happen is if I don't have the workpiece clamped down, when I make this final cut, this outer part of the workpiece will come free, and no telling it's liable to end up through me, or no telling what's liable to happen. So it's clamped down, it's not going to go anywhere. You'll be able to see the end mill here in a second. This is fairly easy to do once you get things set up. Okay, here's the result. I should have cut it about another maybe 1/1000 or 2/1000 around this outer circumference. But that'll almost punch out. There's not going to be any problem getting out and see how this comes out like this. So I will clean that up with a grinder or a file or something. All right, we got that baby out of there. And this is just a little thicker than foil, not much thicker. Got it out without any damage to the part. A little damage to the finger though. This stuff is sharp. Whenever I get a cut, even a little bitty one like that, I immediately go wash with soap and water, and then pour a little hydrogen peroxide in a plastic throwaway cardboard cup and soak it, and do the same thing with alcohol. And then stick Neosporin on it and bandage it up, and by tomorrow, hopefully, keep these fingers crossed, I won't even know it's there. If you don't do that, or if I don't do that, then that baby will be sore for 3 weeks. But we're good. We'll clean this up, and I'll come back, we'll measure that hole. The diameter is not critical. I want it to be about 1/2 inch, so we'll have, because that's what the specs are. But if it's a little over, a little under, that's all right. Let's find out how big this hole is, what the diameter is, more or less. This is a .499 plus plug gauge. It fits. That's minus. 499 plus fits extremely well. I don't think a 500 minus will fit at all. So I hit the jackpot on the diameter pretty close. This is a 500 minus, 0.500 minus. It won't fit. So 0.499 plus will fit, 0.500 minus won't. That makes me happy. Here's what my jig looks like. Went a little deep there, maybe 5 thousandths. You can feel that here. But even here, it's no problem. The next one will bolt right on there and cut it right out. That jig's a I've turned this 1-inch piece of bronze 932 down to length of it down to 0.775, right on the money. It's going to be the eccentric. I'm about to center drill it, step drill it, and then drill it 0.182. I forget what wire bit that is. Then I will ream it 3/16 over. Feel when the flutes get full. This is a number 14, which is a .182 drill bit. Then I'm going to ream it 3/16, which is .1875, but I'm going to bring it 3/16 over, which is .8188, I think, 1885 or something. You might be wondering why I'm doing 3/16 inch on the eccentric when everything else, well, not everything, but the main bearing, which is the only thing, is a 1/4 inch. It's because I discovered that if you do a 1/4 inch on the eccentric, by the time you offset it, you will be right at the periphery of the hole for the main shaft. So what I'm going to ream it 3/16 over, and then I'll take the main shaft, which is a 1/4 inch, and for this section plus whatever I need for the flywheel, I'll just turn it down to 3/16 or to fit this hole. As you can see, the reamer took very little material and gave me a very good finish because I had drilled it to .182 instead of one size under 3/16, which would be 11/64, which would be 0.172. So I got a lot closer. The less material you take, with a reamer, the better the finish is what I've been told. And I believe this finish proves it. I'm almost finished turning the eccentric. You can see this little spot from here to here that hadn't been cut yet. So I'm going to make that disappear, and then the eccentric will be round. And if I make it just disappear, then it'll be the maximum diameter circle that it can be. I want to cut it to fit this eccentric follower link. I want to turn it to that. So let's see what we got. A little tiny bit more to go. Well, it looks round. So we'll measure it. Although this micrometer measurement is pretty much useless. Other than if it's way too big, I'll know how much I've got to go. And it is way too big. It's 525, 530, 3.5. But never trusting anything I do. Still way too big. Okay, that's good. See how she fits. Looking good to me. All right. I need to it's too long. The eccentric is too long by maybe 30, 40 thousandths. It needs to be just maybe 5 or 6 or 8 thousandths longer than the eccentric follower link is thick. So I will skin this down a little bit. I'll bring you back then. Alright, the process is kind of ugly, but I've got a great fit. And got a few thousandths left over on the length of the eccentric. So this makes me happy. 3-jaw to do that. I had to turn off George Jones. But we're going to separate the eccentric from the workpiece, from the raw stock at .34375. It's cut nicely. You almost heard a little bit of Hank Snow, 90 miles an hour down a dead-end street. I hate for you to hear that. Thankfully, the music Nazis are on the job. See, there you go. There we go. Alrighty then. It looks good. Get that off there. Here's why a 1/4 inch main shaft hole in the eccentric won't work. This is to scale. While I scaled it up, everything's 8 times larger than it should be. So this is the main shaft hole right here. And if I want a 1/2 inch throw, that's this circle. It's offset 1/8 of an inch. So that's this circle. Well, notice how it's the two circles are tangent right there. Well, that won't work because we don't have it'll run into the main shaft hole, or it'll be too thin. If they're exactly tangent, it'll be there'll be no material there. So that won't work. However, if the main shaft hole was smaller, say 3/16 of an inch, well, then it'd be over, we'd have this much, theoretically, you know, have that much material to play with. That would work. So 1/4 inch main shaft won't work with a 1/2 inch throw, obviously. Wish I'd have figured that out sooner. All right. Things are going well. This is the eccentric, which turned out well. I need to drill and tap a hole for an 832 set screw. In order to do that, I need to find the center of the eccentric body. I know that the diameter of the eccentric body is 0.7759 inches, and the length of the eccentric body, excluding the eccentric of course, the length of the eccentric body is 0.2772. So what I'm going to do is use this edge finder to find the almost precise center point. And you do that, but you can do that easily, but you have to make sure that if you're doing a round piece like this, you have to make sure that the edge finder extends down to below the diameter. Did I say that right? I think you know what I mean. Now we're going to find the center of the length of the body, excluding the eccentric itself. And the length is 0.2772. I'm going to move the table 0.3886. There's get the tap started by hand. Turning a belt in the drivetrain of the mill. That'll be enough. lower the table enough to get my tap wrench in it. So tapping we will go. Taps easily. Had to get it the right way. Optivisors, that's what they are. Keep them handy. I guess the ultimate test is to see if the set screw will actually fit. Here's an update on where we are, where I am. All the background noise is a fan I've got running and my dehumidifier. I have a 24/7 large dehumidifier, large home dehumidifier that runs continually in here. I've got another one in my other shop area that also runs continually. Electricity is cheap, tools ain't. So that keeps the humidity nice and low in both shop areas. Got the engine block all machined, and the cylinder board, a valve body ring. I made the upright 1/2 inch instead of 1/4 inch on purpose. I wanted a thicker upright than I had on this engine, because I wanted to eliminate the set screw that holds the main bearing in. I didn't want a set screw in there. What I wanted to do is bore a hole for the main bearing in the upright, and then turn a main bearing such that it would be a light press fit into that hole. And I wanted to turn it such that I had that the main bearing is about 50 thousandths of an inch longer than the thickness of the upright. That way I have roughly 25 thousandths of an inch of the main bearing sticking out on each side, which will act as a thrust bearing for the crank disc and the eccentric. And here's how it goes together. Here's my morphodite main shaft, which as I mentioned, I'll never do this again. I wanted the main shaft to be a 1/4 inch, but with a 1/2 inch throw, you can't do a 1/4 inch, as I explained with a drawing earlier, and I hope the drawing showed up. Anyway, the main shaft fits right in there. Slide it way over so we can get everything on. The eccentric follower link has to be cut down here to the right size, but we don't know what the right size is until I build the valve. Right now, the valve looks like this. It'll wind up being about 1 inch long. I made it this long because I have more machining operations to do in the mill. I've got to slit it so that I can pin it to the eccentric follower link, and then I've got to put a hole through it for the pin. But those are later operations. All right, so we'll get it put together. I'm guessing about that much sticking out to hold the crank disc. So I'll lock the eccentric down right there with the set screw. And you can see the eccentric follower link moving up and down. Now you say, well, seal killer. That's what my children call me, and my grandchildren, of course. What keeps it from jumping off like that? Well, the flywheel will have a surface that bears up against the eccentric. And that'll keep it from jumping off like that. That's where we are. It's time to pay some more attention to the actual valve. The stock is about yay long. I think you've seen it earlier. And I've polished it down to where it'll fit in the valve body. Eventually, it has to look like a spool valve. I have to turn it on the lathe and make the diameter in here smaller. But of course I have to also slit it so the eccentric follower link will fit up in there. And there has to be a hole right through the middle for the valve wrist pin. So what do you do first? Do you slit it first, or do you put the hole in there first? Well, I put the hole in there first and then slit it, because when you put the hole in it, if you slit it first and then put the hole in it, then you'll have a burr up in there from the drilling operation. This way, by drilling first, the slitting saw will eliminate any burr there might be. So here we go. Going to center drill. Looks like I might have to lower the table to get my drill bit in there. We'll see. No, it fit just fine. There's a lot of cutting fluid because it's tiny, so we're through. My Canon video camera is down. I've sent it back to Canon for repair. I'm going to try the now seemingly impossible task of using my iPhone 6 Plus to video this some of this work. I've got it on my tripod, strapped to my tripod with cable ties. I know there are mounts for these things, but I'd have to go out and find one. So I'm going to try this, see what happens. My stock is 53 thousandths inch thick, and my slitting saw is 57 thousandths. So that ought to give me plenty of clearance in the piston valve, or not piston valve, but in the valve piston for the stock. All right, I know the thickness of the valve piston, and I know the thickness, I know the diameter of the valve piston. So the saw needs to be positioned at half that diameter. So also I know the thickness of the saw, and I have to take that into account. So if you divide the diameter of the valve piston by 2 and divide the thickness of the saw by 2 and add those two together, you get where you ought to be, and that's where I am. So now I'm going to touch off like for the y-axis to be right in the middle, and it is. So okay, there I'm touching off, and I'm going to make a 1/4 inch in depth cut, 0.250, and I will come back when it's over, because this iPhone tripod thing just ain't working out for me. The cut went just perfectly, and I moved the y-axis back and forth to square the cut up, so we're good with that. And I'm holding the iPhone with my hand, that's why you see it moving around a little bit. I forgot to mention that the cutting that valve piston, cutting that stock with the slitting saw, probably relieves some stress where I cut it, and that allowed the stock to expand at that point. And I imagine that will no longer fit up into the valve body. So I'll have to take that down, hopefully with just some 220 grit, and then polish it up with some 600 using the lathe. I may have to take a little bit off with the cutting tool on the lathe. We'll see. Of course, I'll have to deburr the circumference of the valve piston with a file. I won't even attempt that while holding an iPhone. There it is. Of course, I haven't chopped the valve piston off from the raw stock yet, but you can see that it extends all the way through in operation. See if I can do this with one hand. In operation, it won't go any more than that, or it shouldn't. So the next step is to form the spool valve itself on the lathe. I've decided to create the spool part of the valve next, and to do that I need to reduce the diameter of the workpiece by about 100 thousandths between the base there. You got to find something to point with. Should have had it in my hand. Got to go from about here to somewhere up in here, 100 thousandths, and leave 1/8 of an inch for a head. So what I've decided to do is undercut it 100 thousandths at both places. The place you see now, and then I'll pull it out and undercut it. I think it's 0.6 inches further on down the line there, and then I'll turn between those two undercuts. Obviously, I can't hold the iPhone and do all this at the same time. I've created the spool, and now I'm going to pull the workpiece out a little bit and chop part the spool valve from the workpiece leaving an 1/8 inch head right there. Here's the valve piston. It's 1 1/8 inches of total overall length, and the head of it is 1/8 inch. Fits right down in the valve just fine. If you're making one of Mr. Pete's engines, one of his vertical spool valve engines, the question always arises, or it will arise if you don't make it precisely according to Toly's drawings. The question arises how long to make the upright on the eccentric follower link. It's actually rather easy to figure that out if you've already made the spool valve as I showed you earlier, and if you've already made everything in this order. In other words, the spool valve, the main shaft, the eccentric, and the eccentric follower link. You guess on the length of the eccentric follower link. You guess on it, but make sure you guess long. And then you set the eccentric to top dead center, such that the follower link is as far up into the valve body as it'll go, and that should push the piston, valve piston, way out. And then you merely take your trusty guesstimators here, and figure out how much that is. Guesstimate it, and then that's how much too long the eccentric follower link is. If you take it to the belt sander, or however you're going to do it, and take it down that much, and then drill it at that point. You drill it, we mark it, but take everything apart and stick the eccentric follower link up in the piston, the valve piston, and then mark it where that hole is, and then drill it there. You'll have it at the right length after you've cut it off. Then, of course, it won't rock back and forth as it should as the main shaft moves the eccentric. All you have to do is round the top of the eccentric follower link a bit, and maybe take a little bit more off. I'm going to do that now. Here are both valves at bottom dead center. On the left is my previous engine, which you've seen running. Bottom dead center, the valve is down 0.247, and the current engine, the valve is down 0.249, so virtually the same. On the right, you see the wrist pin hole that I just drilled for the wrist pin in the valve. I located it by just sticking the eccentric follower link up into the slot in the valve and marking the spot with a pointer thingy. I should mention that I drilled it 1/16 of an inch. The wrist pin hole in the valve is the 1/16 of an inch, and the wrist pin, which I've used a dowel pin for a wrist pin, is a 1/16 of an inch in diameter. So it's got to be pressed in there, and pressed in there while the eccentric follower link is in the correct position in the valve. So I will use my vise to do that, and of course, since I'm doing this via iPhone, you won't be able to see it because there's no way to do it with one hand. Right, it went in there nicely. Plenty of movement, as you can see. I'll take it down to the belt sander and sand the excess off of the dowel, wrist pin, and everything will be fine. Well, there we go. Let's see if I can get it into the engine block now. It's hard to do with one hand. Oops, there's a critical part, went right in. Now, to assemble it, you slide the eccentric follower link, or the eccentric, into place, which I really can't do with one hand, and then stick the main shaft in. And there we have it. Can you see the piston? The valve, I mean, moving up at the top of the block there. There needs to be an intra-cylinder or intra-valve cylinder hole between here and here, located 0.2 of an inch below the surface. That allows steam, or in my case air, to move from the valve to the cylinder, and air exhaust from the cylinder back through the valve into the atmosphere. Of course, this opening is only necessary to drill the hole, and has to be closed later. And the way you close it is, or the way I closed it on this engine, was stick a set screw in it. And I did not file, or rather belt sand, this set screw off with the surface of the engine to the surface of the block, but I probably will with this one. And there's the hole between the valve and the cylinder. Wow, I almost screwed up by not turning my stereo off. I had Ray Price going. The YouTube Nazis would have killed me for that. So there is the intra-valve steam port, and I've tapped it 832, and I'm going to put this 3/16 inch long set screw in it. I open this side of that hole between the surface and the valve to 0.136, which is the number 29 word number drill, and tapped it for an 832 socket head cap screw, or set screw, and it's protruding a little bit. I think I'll leave it protruding because I've got plenty of space to drive it to screw it in there and not protrude. I'm going to Loctite it, leave it protruding, and then when I clean up this surface, it will grind it flat. Or maybe not. Maybe I won't do that, because then it'll be harder to get out if I don't have that entire inner shoulder to play with. I think I'll screw her in a little bit more, Loctite it, screw it in a little bit more, so that it's below this surface. And then when I clean it up, I'll still have that entire shoulder of the set screw to play with if I ever need to take it out for some reason unknown. I Loctited this 832 set screw in. The shoulder of the set screw is below the surface of the block. The crank disc is next. I'm going to build it out of this piece of 1 1/8 inch diameter of aluminum. The crank disc will be 1 1/8 inch, but I'll probably take a light skim cut on the circumference to make it nice and shiny. I'll face it off now and then center drill it, step drill it 1/8, drill it 15/64, and then ream it a quarter over, and then I'll cut it off. Great. Clean that part up, and we're good to go. I'm going to center drill the crank disc, drill it number 29, and then tap it 832 for a set screw. I turned off Conway to make this segment, so it's going to be real short. Both the crank disc, which doesn't have the crank in it yet, and the eccentric bear upon the main bearing surface that sticks out about 25 thousandths of an inch. You can kind of see it right there, 25 thousandths of an inch on either side of the upright. That's what I was shooting for. To eliminate, I wanted to eliminate the spacer that the original design calls for. You see that spacer right here. I wanted to eliminate that, and I wanted a wider upright. I need to put a hole in it about right here, 3/8 inch from the center of this one for the crank pin. But I have to find the center of the crank disc first, and the way I'm going to do it is by moving the table until this 250 minus plug gauge fits, and I'm going to need 2 hands to do it. So as soon as when it fits, that's the center, and then I'll offset the table 3/8 of an inch to create this hole. The plug gauge fits in there nice. It's a good fit. So I'm in the center now. I'll offset the table 3/8 of an inch. When I turned the piston stock prior to cutting that slot, I got just a very nice fit in the cylinder. But cutting that slot relieved some stresses in the 4140 and allowed that section of the piston to expand by 3 10,000ths, or maybe 4 10,000ths. Now it won't fit. So I'm going to polish it back down with some 220. I hope I can polish it down instead of turn it down. Because if I turn it down, I've got to deal with that interrupted cut. We'll see. It's going to go down one way or the other. Okay, we got a nice fit. I took at least 4 10,000ths off. I mic'd it at 0.4971, so I took off 3 10,000ths with 220 grit sandpaper and then polished it up with 600 grit. I'm going to part the piston from the workpiece. There's the piston. Has a nice fit. I'll do the flywheel next. I cut the connecting rod out of a piece of 0.052 inch thick brass plate and kind of shaped it on the belt sander. I've got the wrist pin location marked with a center punch. I'm going to center drill it and then drill it 0.120 and then ream it 125 for the wrist pin. All right. Here's the piston and the rod, connecting rod. Now the shape of that connecting rod is just kind of up to you. I made mine narrow at the top, maybe not narrow enough, we'll find out in a minute, and wider at the bottom. Notice there's no hole in the bottom, wonder why. How long is this connecting rod supposed to be? Well, I don't know. You won't know either till you build this assembly right here. And of course, have at least the main shaft and the crank disc in it. You'll fit the piston and connecting rod to the crank pin. You'll mark the connecting rod at the proper place. When the piston is at top dead center, the main shaft, the crank pin needs to be at top dead center. And you know when the piston's at top dead center because you can see the inter-cylinder valve hole or steam port. See, this piston is quite a bit below top dead center. Let's see if I can make it top dead center with one hand. All right, now it's a little bit below top dead center. I'll shove it up a little bit more, then mark the connecting rod at the right place. I'll pull the connecting rod out and slip that crank disc pin under it, and at that point I'll mark it. In fact, if you look, you might be able to see I've already done that. And then I'll drill the hole for the crank pin at that location. In Toly's drawings, which I try to follow, modified. This engine is modified from that though. He made an improvement to the crank pin rod interface by sticking a 5/32 inch brass tube in there, 5/32 OD. So I did that, not exactly like he did it, but it's in there. I pressed it in there, and now I'll bring this out and slip it over the crank pin. Let me see if I can do this with one hand. Everything moves nicely. Well, it's not totally nice. There's a little tight spot in it that I will eliminate when I get the flywheel built. The toly's bushing idea worked nicely as I modified it. Yeah, I'm sure it worked better the way he did it. When you have it set on top dead center, as it is now, you can see the piston is just below the steam port. There it goes back down. So, looking up, flywheel's next. This 3-inch diameter piece of aluminum will be the flywheel. The flywheel will be 1 1/4 inches wide. So I'm going to face the both sides of this piece of aluminum now. I've turned the workpiece down to 1 1/4 inches long. It's 3 inches in diameter. Now I'm going to center drill it 7/64, drill it number 13, which is 0.182, and then ream it 3/16 over. I've got the short side of the hub turned. It's 1/4 inch long, 1/2 inch diameter. Now I'm going to turn this workpiece down to create the long side of the hub, which will be 1/2 inch long and 1/2 inch diameter, of course. That'll leave me with a flywheel width or length, what would you call it, of 1/2 inch. There's the flywheel, all except for cleaning up the outside surface. It's got a 1/4 inch long hub on this end, on that side, and a 1/4 inch, or not a 1/4 inch, but a 1/2 inch long hub on this side. The 1/2 inch long hub will let me drill and tap it for a set screw, and after I do that, I'll put it on a 3/16 inch arbor, and just a 3/16 inch drill rod. Stick it in the back in the lathe and lightly touch up the periphery, the circumference. So that made me happy. Quite a bit of aluminum came off that piece. As it started off as a little over 1 1/4 inches, and it's 1/2 inches wide, 1/2 inch wide. So there we go. Good news and bad news on the video front. I got my Canon camcorder back from repair, but they failed to send the charger. So it's virtually useless without the charger, and theoretically the charger's in the mail. We'll see. I need to put a set screw in the hub. I'm going to put an 832 set screw in there, so I'm going to center drill it number 29, and then tap it 832. I laid out the head bolts with a square and a protractor, and I'm more or less happy with the layout. Now I'm drilling and partially tapping. Can't tap all the way because I don't have enough room to get my vertical height, to get my tap wrench between the chuck and the surface of the block. So I'm partially tapping, and then later I will finish tapping. But once I get the thread started, there's not any danger of getting in there sideways or anything like that. There's going to be 8 head bolts. It doesn't have to be 8. 4 would be fine, but I just thought 8 would look neat, and the head's going to be square. I should have mentioned that the reason I can tap now, just the several threads, is that I'm turning the spindle by hand. There they are, tapped partially. I'll move the table so I can get to it with a tap wrench and finish tapping. The 2 in the middle, like this in the middle, they're not perfectly in line. And that bothers me, but it's done now. I'm going to take 5/1000ths off the surface of the block there to remove the layout marks. That cleaned up nicely. Okay, there's the surface of the block with the transfer screws inserted. And here is the head to be. It's too wide in all dimensions for the block, but I'm going to transfer the holes and then transfer the location of the holes, and then drill clearance holes here in the head and bolt it down to the engine, and then make the sides anyway, and the front over here, congruent with the block. I forgot to say that I'll use the vise to actually press the head into the transfer screws. Can you see the 8 marks in the head? That's where I'm going to drill the 440 clearance holes with a number 32 drill bit. I'll drill 3 holes, then move the parallel, drill 3 more maybe, and then move the parallel and drill the other 3. I have to turn the piece 90 degrees, but we'll get her done. This is what it looks like. Unfortunately, I missed a hole, so I'll fill that hole in the block up with JB weld and then re-drill it and tap it. I don't really need it, but it would look nice if there was a screw there. So the next operation is to clamp this thing in the mill, in the vise, and square the corners up with the surfaces of the engine block. There, how's that look? After considerable head scratching, I figured out a way to move that hole over a little bit. So now we're good. If I can do this with one hand, it's going to be first steam. I think I've got it timed wrong. Well, there's first steam. After I got it timed right, I timed it according to the way my other engine was timed visually. But the problem is the main shaft is bent. I've got to build a new main shaft. So it's running on just a few pounds of air. It's pegged on 0. I'd say maybe that's 3 pounds. I'm going to lighten that flywheel up and fix the main shaft. A straight main shaft makes a big difference. So it ran on first steam, even though the main shaft was bent. I don't know what it's running on. It's less than what my gauge will register. Well, here are all the parts. Let's see if some of them will fit. As you can see, I've got the engine mounted on its base with its feet. Also, the main bearing is pressed in there, of course, but that's it. And I'm going to try to assemble this thing on video. I will fumble around, I'm sure. You just have to forgive me. Or not. Let's stick the piston in there. Notice the bearing I put installed on the connecting rod. That's kind of a modification of Toly's idea, and I'll give you Toly's email address with plans of an engine fairly similar to this later. Got to kind of bend this out to get it over the crank pin. There we go. And now before I put the flywheel on, I wanted to point out that the main bearing protrudes beyond the width of the pedestal by about 25 thousandths on each side. That allows, that provides 3 bearing surfaces, not only the traditional main bearing upon which the main shaft turns, but if there should be any in and out play, then the crank disc will bear upon the one end of the main bearing, or the eccentric will bear upon one end of the main bearing. So here's the flywheel that I turned as one piece, and I'll lighten up on one side. What I'll do is I'll take some weight out of it in an attempt to balance this engine a little bit later, and after that then I'll try to make it cosmetically a little prettier. going to time it from, let's take that back off. I'm going to time it from memory here. Well, actually, you don't care about the timing because you just want to see this thing put together, don't you? Let's time it anyway. Trying to get it on bottom dead center. Now I know when it's on, when the eccentric is at bottom dead center and the crank pin is in that location, then it's timed where it'll run. I think that's it anyway. Nice and smooth. I'll stick the head on it. One extra long screw because of a little screw up I made. And one extra short screw instead of a 1/2 inch screw. This is a 3/8 inch head bolt. It's short because it has to miss the inner valve steam port that goes from the engine to the valve. So there it is, other than tightening the head bolts. There it is, it's finished. I've played with the timing, and this is the about as slow as I can make it run. It's easier to make it run fast, of course, than it is slow. But people seem to like slow better than fast. I'd like to mention that this is an adaptation of one of Tubal-Cain's engines. It differs in a few aspects, but basically you can watch his videos and build his engine, which will look a whole bunch like this engine, except he sinks his flywheel down into the base here, which is an attractive thing, but I wanted my flywheel up. I did that on purpose. And I have some vague plan to one day build one of these engines and put a belt around that flywheel, or maybe I'd extend the main shaft and put a pulley on it. I just don't know. This engine has a .497 inch bore, which is as close as I could get to ½ inch, or as close as I wanted to get to ½ inch, without going over. This engine, which works equally well, has a .8 plus .830 inch bore. Takes a little more hair to run it, but not much more. It probably runs on 2 pounds. The one not in the video right now probably runs on 2 pounds of air. I'm guessing this is running on 2 pounds of air or less. Toly's drawings are invaluable in building an engine like this, and I will provide his email address for the plans, for the drawings, at the end of this video, and he'll be glad to send those drawings to you should you send him an email requesting them. You might notice that my flywheel is different. It was solid. I never had plans to leave it solid. I wanted to lighten it up and do just, whatever little cosmetic work I could do to make it prettier. In lightening it up, it made for a more responsive engine. It starts easier, a tiny bit easier, but it just accelerates faster. You can see the valve action there. I don't have the spacer that Tubal Cain's engine has between the eccentric and the upright. I purposely eliminated that. It's easy to eliminate it, but you have to pretty much eyeball the distance from the upright to the center of both the valve and the center of the piston, so you can get the eccentric the correct width, and so you can get the crank disc the correct width. Now notice the crank disc is probably not critical anyway, because as long as it's small enough, the connecting rod connection interfaces got plenty of play in there, or plenty of space to move back and forth. But this is critical. You want I've got a bearing surface on the crank on the eccentric. Wonder what I dropped. This bearing surface on the eccentric must bear on the flywheel to keep the eccentric follower link from coming off. Next time around, I'll make this hub a little bit larger, or maybe the same size as the eccentric. Probably, no, I'll make it larger. And that way it will bear on the eccentric throughout the eccentric's travel. As you can, I don't know if you can see or not. Let's see, let me look through the camera. Nope, I don't think you can see. The eccentric and the follower link stick up above the bearing surface of the hub at that point. But I mean, it's not about to come off, so it's really no problem. My head is square. I decided I like that square look. It gives more of a machine appearance. And I put 8 head bolts in it, not because it needed it. This design runs fine without leaks with 4 head bolts. But I like the way that 8 head bolts looks. And I like the square head better than the round head, since we're dealing with square surfaces, square areas there. The crank pin bearing is another takeoff on Toly's idea for a crank pin bearing. Mine is simpler. You can read that as easier to make than Toly's. It's just a piece of brass tubing that fits right over that crank pin and is pressed through a hole in the connecting rod. I reamed the hole in the connecting rod, but there's probably no need to. It could be drilled. The only mistake I think I made on this engine is one that I overcame with just by turning another piece. But I wanted a 1/4 inch main shaft instead of the 3/16 inch in Tubal Cain's engine and in Toly's plans. Well, that sounded real good, except with a 1/2 inch eccentric, a 1/4 inch shaft, main shaft, would be tangent to the inside of the eccentric. In other words, the eccentric follower link, during at least, technically, at least one point, a single point in its travel, would be bearing on not the eccentric, but on the main shaft. So that's no good. So what I had to do in order to continue to utilize the main bearing that I'd already built was build a main shaft in 2 diameters. One diameter from the crank disc through the main bearing is a 1/4 inch, but from here all the way out to the end of the flywheel, it's 3/16 of an inch. To turn that shaft is relatively easy. You just have to make sure that you support the end of the shaft with your tailstock on the lathe. If you watched this whole video, you saw the original main shaft in there with the flywheel wobbling because the main shaft was bent. However, the engine ran fine. As Tubal Cain said, it's hard to make one of these engines not run. So that's it. This is what she looks like. Get a little rubber feet on it. This is the finished product. the guy I'm going to give it to liked the tool marks in the both the engine and the base. Gave it more of an industrial feel, an engraved look. He's a gun guy like me. Than a highly polished finish would. And it also demonstrates how well trammed my mill is. The main bearing, which extends through this upright, is 50 thousandths of an inch longer than this upright is wide. 25 thousandths protrudes on this side and 25 thousandths protrudes on this side, and that gives me a bearing surface for side play like this, in case the main shaft works to the left or the right, then it's bearing on, it's got a thrust bearing surface created by that main bearing protrusion. I like that idea. That was my idea. I hope this video has been helpful. Build one of these engines. They're easy.